Okay, we're going to start? Thank you. Today we're going to go through some proofs, and these demand a lot of attention, and yeah, I forgot the chalk. Let me get the chalk. So I think in the middle of the lecture we'll want to stop and hear this story. Anyway, what we want to do now is higher order non-degenerate perturbation theory. And we've done first order degenerate and non-degenerate perturbation theories, and now we want to do higher order non-degenerate. And so what we imagine, let's just set the notation. We're going to have a superscript 0 here, meaning that N0 is the eigenstate, is the nth eigenstate of the Hamiltonian H0 that we understand. On the other hand, the Hamiltonian that we want the energy levels and eigenstates of differs by a potential, which is of course a Hermitian operator, multiplied by a small dimensionless parameter. And so the equation we seek to solve is H0 plus lambda V on some state n is equal to E sub n. So that's the goal. And we want to find these En as En0 plus lambda. And let me see, there's a notation here that I should, I'll be getting to later in the lecture, but I might as well say what it is at this stage, if I can find it. I want to get the lambdas in the right place. It's a power series in lambda, so this is N0 plus lambda N1 plus lambda squared N2. So that's how the other ones go. And unfortunately, I don't have a notation for this. What we say is instead that delta n, which is En minus En0, is going to be lambda delta 1 plus lambda squared delta 2 plus dot dot dot. So that's actually, even that's not quite right. They're superscripts. One, two, and 10. So we're going to be looking for the energy shift of the nth level, and we're going to be expanding that as a power series in lambda, and we're going to be expanding the true eigenstate as a power series in lambda. So that's the goal. Now, at the very beginning, what we can say is that this is then going to be equal to delta n plus En0 on n. And as we saw last time, if you take this equation, the left-hand side equals this right-hand side, and sort of mix things around, what you get is En0 minus H0 on n is equal to lambda v minus delta n on n. And in particular, this tells us that that 0, of course, is n0 on this to the left, en0 minus h0, and because the n0 is an eigenstate of h0 with eigenvalue en0, so this cancels. And that means that n0 is orthogonal to this state, lambda v minus delta n on n. So orthogonal to n0. This is something that we'll be using later. It may not be apparent why it's such an important thing at the moment. One reason kind of is that means that this operator has a zero eigenvalue, so we can't just form the inverse of that operator. We can't just say n is 1 over. In other words, we can't just say n is 1 over en0 minus h0 on lambda v minus delta n. So this won't work. No, it won't do. On the other hand, we can do something close to it if we just avoid this energy level n0 that is a 0 of this operator. And then this division will be okay. And the way we're going to do that is we're going to use a projection operator. My notes have used a Greek letter. I'm going to switch to a projection operator. It's sort of an orthogonal projection operator. It's 1 minus n0, n0. And 1 then is the sum on all these states. Let me call them k. So we subtract the dyadic n0, n0 from the identity, and that just gives us the sum k not equal to, I guess it's k not equal to n of k0, k0. So this is a projection operator that's orthogonal to the state that's the nth eigenstate of h0, n0. And that projection operator then behaves like this. 1 over en0 minus h0 pn is the same thing as pn 1 over en0 minus h0. And it is just the sum of k not equal to n of k0, k0 over en0 minus ek0. That is to say, these k's are eigenstates of h0, so they just kick out a k0 down here. So this is a structure that we can deal with. Sorry about my eyes. I'm going to get some allergy to everything that grows in New Mexico. So what are we going to try? Well, we're going to try, instead of trying this, we're going to try the following. We're going to say that n, in fact, there's sort of a song and dance here in the notes, but it seems to me that we can deal with this later. I'm just going to write it this way. So this is the equation that we expect. In other words, instead of this equation, which is kind of right in spirit. We're going to put in the projection operator so that this inverse operator makes sense. And then we're going to take advantage of the fact that when as lambda goes to 0, this coefficient here, the state goes to n0. Now, literally, we should put in a parameter here that depends upon lambda, but that only affects basically the overall normalization. So, and we're going to set that equal to 1. That's just to simplify the notation. So the state n that we find by this equation, solving this equation, isn't going to be normalized, but we can worry about that later and normalize it. So this is the equation that we want to solve, and we now know that just over here, this equation which we use to motivate this song and dance actually tells us something. It tells us that of course the equation was 0 is n0 lambda v minus delta n, that's equal to 0. But that is just the that is just n0, or rather, let me just be a little more careful here. Lambda is a constant, so it's n0 v n minus delta n, n0 n. But n0 n is 1 here, and it's 0 over there, so it's just 1. And so we get the equation delta n is equal to lambda n0 v n. Okay, so that's in fact an exact formula for delta n. And we're going to use that as one of our equations. Now, what we want to do is we want to check that this gives us a state n that, although unnormalized, is nonetheless an eigenstate of the total Hamiltonian H0 plus lambda v. And so what we're going to do is we're going to take En0 minus H0 on n, and that is going to cancel this first term. It's going to cancel that, and this is going to be equal to P sub n times lambda v minus delta n n. But on the other hand, we know that lambda v minus delta n n is orthogonal to n0 anyway, so this projection operator doesn't have any effect. So we can rewrite that as lambda v minus delta n on n. That is to say, lambda v minus delta n is already orthogonal to n0, so adding the projection operator that projects onto the space, the subspace that's orthogonal to n0, has no effect. And now if we just unscramble this equation, what we see is that this tells that we move the H0 over here and the delta n over there. We just see that that's the equation. H0 plus lambda v on n is equal to E0 plus delta n, which is to say equal to En. So indeed, this, if we solve this equation, what we have is a solution. We have an eigenstate of Hamiltonian, not normalized, but it part of normalization, which is always a So by comparison with everything else, it's a trivial thing to do. And so what we want to do now that we've set the stage for things, is we want to write delta n, which is the energy shift of the nth level, as a power series in lambda, and we want to set the unnormalized exact eigenstate of the nth eigenstate of the total Hamiltonian. Remember, this is a non-degenerate problem where essentially assuming all the levels are non-degenerate. Although the only one whose non-degeneracy plays any role in this, as far as at least as far as we're going to get in this series, is the nth level. The others could be degenerate. Anyway, we're expanding that as a power series in this small dimensionless parameter lambda. All right, now let me erase some of this. Are there any questions with this? Remember, I have candy in case anybody does ask a question. By the way, I should mention something. Next week, I have to go to a conference on biophysics in Boston, and it turns out that's going to overlap. It's going to kill the class on Monday and Wednesday. So the good news is there's a holiday in this course. The bad news is that we're going to have to make up the classes later at some point. It's such a small class, we have a lot of freedom there. We could make them up during spring break if you want. But why don't you guys think about when you want to make up the classes?
If they extend stuff, which is like
we could do them on Tuesdays, on Saturdays, or we could do some extra classes during the exam week. Instead of having an exam, we could have a class, and so forth. We have a class on the... So think about it, and send me email and talk with each other. There are, not that many of you, so you did pretty well. Get that straightened out. Any questions? All right, maybe this is the time to tell the story. Berg and Purcell both won Nobel Prizes. Purcell certainly in physics. Berg might have won his in medicine and physiology, or it might have been in physics. At any rate, Berg went to medical school at Harvard, and he hated it. And after a year or so, he dropped out, and he started hanging around the physics department at Harvard. And he came to admire Professor Purcell, who was a marvelous lecturer as well as a Nobel laureate in research. And there were things like NMR, and which became MRI, credited essentially to Purcell, and I think he may have been behind the 21 centimeter observation of the 21 centimeter line of hydrogen, galactic astronomy. In any event, Berg went to see Purcell and said, "Professor Purcell, could I work under you as a student?" And Purcell said, well, he didn't think that would be a good idea because he didn't know what to do. In other words, Purcell said to Berg that he wasn't sure what to work on, and so it wasn't a good idea for Berg to become a student because he didn't know what to work on. And I just find that a remarkable story because one thing that it shows is that Purcell, instead of just working on whatever was an easy problem that he could knock off and make a paper, he was looking for something that he thought was worth working on. And that required him to remain fallow for a while and just think and find a problem. And then after he found the problem, then he start working on it and look for a student or more, or students who would work on it. Anyway, that's a story I heard from Berg. I think it was during, no, I think it was either an after dinner speech or I met him at lunch and told me that story. Anyway, it's an interesting story, I think. So in particular, we can take this sum then of this power series and lambda expansion of the exact eigenstate, and we can stick it into this formula, and what we get then is lambda n0 v times n0 plus lambda n1 plus dot dot dot. And so that tells us that delta n is the sum. I have this written as k. That's probably a bad choice here. Let me call it L. L equals 0 to infinity. L here is not angular momentum. Lambda to the L plus 1 n0 v n L. So that's our expression for the energy shift. Of course, it doesn't do us any good at the moment, except when we recognize that if you set L equals 0 here, then indeed that is the expression for the first order energy shift. Let's see, well, it gives us the expression for the first order energy shift. In other words, delta n0 is in fact simply n0 v n0. So that comes out of that. In other words, the general formula here is the Lth term is n0 v n1. Okay. Now, what we want to do is substitute this expansion here and that expansion into our eigenvector equation here. And when we do, what we get is a sum, say L equals 0 to infinity, lambda to the L, and L equals n0 plus Pn over En0 minus H0, lambda V minus a sum. And I see in my notes I switched to L in this term, so let me call that P. P equals 1 to infinity, lambda V delta P to N on sum J equals 0 to infinity, lambda J and J. Okay, so this is this equation which we've checked is okay, gives us the right answer, together with these two power series solutions, power series expansions. Now, in fact, it's just a matter of requiring that the coefficients on each side, in other words, what we get out of this effectively is an infinite set of equations, one proportional to lambda to the 0th power, then lambda to the first power, lambda to the second power, lambda to the third power. We get an infinite set of equations. Equivalently, we could differentiate this equation with respect to lambda of 0 times, 1 times, 2 times, 3 times, 4 times, and then set lambda equals 0, and we get an infinite set of equations. Because this is supposed to be an equation that's true for all real lambda small. On the other hand, we know that Pn on delta n, n0 obviously is 0. And so, in particular, when this thing goes along here, this Pn, it's going to knock off when it hits these guys, it's going to knock off the J equals the 0 state. And so you can simplify this a little bit. It's the sum L equals 0 to infinity, lambda to the L, n sub L equals n0 plus, so we're going to split this up a little bit. It's going to be Pn lambda V n0. So the n0 state, in other words, only survives when protected by the potential from the projection operator. So this is En0 minus H0. And that's actually a bad way of writing it. Let me rewrite it. Lambda V n0. Okay, and then the rest of it is plus P sub n over En0 minus H0 lambda V minus a sum. And now we can go from J equals 1 to infinity. Whoops, that's bad parentheses. Okay, so now this is our equation. All right. So if we look at this, suppose we differentiate 0 times, which is say do nothing, and just set lambda equal to 0, then what do we get? We get from this term, we get n0 equals n0, and then over here, we just get 0, we get 0, we get 0. So this thing is consistent at the lambda equals 0 level. What about lambda equal to 1? Well, lambda equal to 1, we get lambda n1, the first correction, equals P sub n over E n0 minus h0 times V times n0, well, lambda V. And then, let's see, there's the rest of this actually cancels, but, yes, the reason why, you guys should have called me on this. I did not write this correctly, I skipped a term here. It's lambda V minus this sum, P equals 1 to infinity, lambda to the P, delta P, n times, sum, now J equals 1 to infinity, lambda J and J. Okay, guys, you're not paying any more attention than I am, so the 6 of us have to shape up here. All right, so lambda equals 1, and what you see is since this has a lambda in it, and these guys both have lambda, this is the lowest order on the right here is lambda squared. So it doesn't contribute. And this gives us a formula for the first order correction. And so the formula for the first order correction is obtained just by erasing lambda. So in other words, if I erase lambda here, I get this expression. So, now what we've got then is we've got the, actually this was a mistake, you should have called me on this also. This is a 1. Isn't it a 1? Let me just make sure there's this damn nomenclature here. It's a little bit, okay, delta L is L minus 1. Yeah, this is delta 1. So we found earlier that the first order energy shift is just the mean value in the mean value in the end state of the potential. And now we find that the first order correction to the eigenstate is the projection operator on the space orthogonal to the nth level. This thing here, which we could call a propagator, the potential, and then the state. So, in a sense, we've gone. I mean, we haven't solved the problem, but we've gone way into it. That is to say, we have these are frankly the things that are most used. This is the equation that's in fact the most useful. It's also the simplest, and it's often true that the simplest thing is the most useful thing. All right, now we want to go beyond that. Any questions? All right. Now, we already have a formula over here for what delta Ln is. Namely, it's N0V and L minus 1. But we now have N1 here. So that means that not only do we have the first order energy correction, but the first order correction to the state almost immediately gives us the first order correction to the energy. And so that means that delta 2n is equal to N0 V N1, and that's going to be N0 V En minus H0 V N0. And if we insert a complete set of states, then what we find is delta 2n is equal to a sum k9 over n, that's because of the projection operator, N0V, K0, K0, and the K0 gives us the energy down here, En minus K0, V N0. Or writing it in a somewhat nicer form, it's K0, V N0, absolute value squared, over En0 minus K0. Okay, so that's a very nice formula for the second order energy correction. Frankly, it's rare in ordinary quantum mechanics problems that one goes beyond this. You normally stop here. And you can see why, because this in fact is an infinite sum. And that's not a piece of cake, an infinite sum. And if you're dealing with a harmonic oscillator, then you can probably bang this out without any trouble if V is completely pathological. But if you're talking about the hydrogen atom, then this is another matter, because these get to be pretty complicated functions. And in fact, it's even worse than it looks, because this sum here, this projection operator, is the identity minus that state. But in the case of the hydrogen atom, the energy this projection operator would not only be the sum over the bound states, but would be the sum over the continuum states. And that's a big deal. Schwinger worked it out in various cases, but most people pass on to some other problem. All right, now let's look at this and learn something very simple. Namely, let's look at the second order correction to the ground state. Remember, we're always in the case here where the the ground state. We're in this case where this end state is non-degenerate. So it's K0V N0 absolute value squared over E10 minus EK0. So EK0 is going to be greater than E10 because EK is one of the excited states. And it's the non-degeneracy, that's coming in here, among other things. In fact, let me just mention about the non-degeneracy. You see, this particular form of the projection operator, of the identity operator, minus just a simple dyadic, that's only possible if this nth state is non-degenerate. Otherwise, we have to subtract not only N0, but N01, N02, N03 if we're degenerate. Similarly here, all right, anyway, these are the excited states. This is the ground state, so this is always negative. So this whole thing is less than 0. So the second order correction to the ground state energy, no matter what the potential is negative. That's by the way, a favorite question on we have these various exams, preliminary, qualifying exam, comprehensive exam. That's a favorite question on CIP exams. And I'm opposed to those kind of exams. Anyway, word wise. Appreciate this equation is your friend. Being on a first name basis. Okay. Now let's look for N2. Well, we're going to go back and that's what I meant to say. Oh, sorry, yeah. We have an expression for N1 now. And we can put that expression for N1 in. You see, over here, we so far got away with we got away with how shall I say it? In this expression, we need to know what N1 is to go beyond it and find N2. And so what we're going to do is look at the lambda squared expression in here. And so if we do that, what we get is lambda 2, the second order correction for this nth energy level, and it's Pn over En0 minus, it's supposed to be H0, minus H0. And so this one obviously doesn't contribute. This one here can only contribute one factor of lambda, so it's out of the picture. And now this one can contribute along with that. And so what we get here is lambda d minus lambda delta n1. So we necessarily have one factor of lambda here, at least one factor of lambda. And so over here we want exactly one factor of lambda. And so what we get there is lambda n1, but we already know n1, namely n1 is given by this expression here. And so now we can substitute for that expression, dividing by lambda squared, we get n2 is equal to p sub n over e n0 minus h0 v. Okay, I'm going to separate these two terms. And now n1 gives us a p sub n over en0 minus h0 v n0. So that's the first term. And then this one gives us a minus p sub n over En0 minus H0 N0 V N0 P sub n V N0, and then over, let me put this over to the left here, En0 minus H0. In other words, we have to use, first of all, our expression for delta 1n. Our expression for delta 1n, you remember, was N0V N0. And so that's the ends, this is delta n1, so this is a comment parentheses, not part of the equation. Maybe I should do this. That's delta n1, and then n1, the state, is Pn over En0 minus H0 Vn0, and so that goes over here. So that's the expression for N2. So it's a kind of unwieldy. Not that unwieldy. You can see that this isn't something that going beyond second order is going to be certainly a chore. That's obvious. All right, let me erase this and write this in a couple of different ways. So there are two more ways of writing this. N2 is a sum on, let's say, K and L, not equal K0, and in other words, we've got these V's here, and this is going to be a sum over the K0s, a sum over the L0s. So we're going to get expressions of the form K0, V0, K0, VL. So we're going to say K0, V, L0, and we're going to write as VKL. And so this is VKL over ENL minus EK0. And then VL N, because we're going to have an N0 V L0, so that's VLN, and that's going to be E N0 minus EL0. So that's this term, and then it's going to be minus the sum K naught to N. So in this term here, we just have one sum. And that gives us a K0 and VNN. This is the same thing as VNN in this notation. And then the VKN from this projection operator here. And in fact, these two projection operators, since this is just a number, these two projection operators just become one projection operator. So this, in other words, as for any projection operator, Pn squared is equal to Pn. Does anybody, you guys want to see this? And then what we have here in the denominator is En0 minus K0 squared. And, all right, a slightly better way of writing this is a sum k not equal to n, k0 over en0 minus ek0 times a sum L not equal to n, DKL ELN over En0 minus EL0 to n minus ENN BKN over En0 minus EK0. So this sum only includes that term. Okay, so that's another way of writing it. So these are all numbers, and these are the only vectors. And of course, you can go on, but we won't, because it just gets more and more elaborate. So what is the energy eigenvalue? Well, it's En0 plus lambda times N0V N0 plus lambda squared times the sum k not equal to n. And in the notation that I've been using, this is Vkn, absolute value squared, over En0 minus Ek0. And apart from normalization, n is equal to N0 plus lambda Pn over En0 minus H0V N0. Oh, let me just write plus lambda squared into, I really don't want to write that whole thing, especially on my knees, but that's what it is. In other words, it's N0, this first order correction is already sort of complicated, and then lambda squared times this N2, which is written there. All right, so let's think about that for a second. All right, now there's an observation that we can make, very general, and that's worth knowing about and thinking about. It may also be another favorite of these awful exams, a question for pure awful exams. So suppose we have two levels, top, which we call T, and B, the bottom. And of course, what we mean here is that T0 is greater than EB0. Okay, so what's the second order change? E2 top due to bottom. In other words, if we look at these energy shifts, we see that the energy shift on the nth level is due to all of the other levels. In particular, this expression here is the energy shift of the nth level, the second order energy shift of the nth level due to the kth level. And then you have to sum over k is not equal to n. So the shift of the top level due to the bottom level is going to be equal to the delta 2 part, in other words, apart from the lambda squared, is going to be equal to E0V P. In fact, I would just, since we introduced this notation, we might as well take advantage of it. It's going to be T BT or TB, it doesn't really matter, squared over, and this matters, it's going to be ET0 minus ET0. So the n occurs to the left. And delta 2 of the bottom level due to the top level is going to be the same numerator, et squared over EB0 minus ET0. So the point is that the second order shift for the top level due to the bottom level and the bottom level due to the top level, in magnitude they're the same, because these absolute values are the same. And the denominators also in magnitude are the same. So these things in magnitude are the same, but they're, what are they? This is positive, and this one is negative, because, so this is less than 0, and this is greater than 0. Or to write it differently, this is equal to the absolute value of delta 2 TB equals the absolute value of delta 2 BT, and this is equal to minus the absolute value of delta 2 TB, which is minus the absolute value of delta 2 BT. So this is negative, this is positive, and so what you say is that as you turn on the perturbation, the effect of the second order, these levels, which might have been here at lambda equals 0, they change in various ways, but when you get to the lambda squared, they repel each other. And how do they repel each other? Well, the closer the two are to each other, the smaller this denominator, the more they repel each other. So nearby levels repel each other. But any pair of levels is repellent in second order. All right. Okay. So now let's get to another topic here. I wish I had come with more jokes and stories. I seem to be out of jokes and stories. I usually have a full raft of tangents, but I'm not in it. So not sometimes. All right. The normalized exact energy state, we're going to say is Z sub n to the 1/2 times the thing that we've got that's not normalized. And this is a notation borrowed from renormalization theory. So that, and 1 then is equal to n sub n. And that's going to be Z sub n to the 1/2 times n sub n, n. Okay. So this is the unnormalized. And we've said, we took as a condition that n0 n was equal to 1. That's the way we set it up over there. By that equation way up there. So what is n0 n? So n. Well, n0 n sub n then is z sub n to the 1/2 n0 n. On the other hand, that is itself equal to 1, so this is just dn to the 1/2. So the way we've set things up, n0 n normalized is z to the 1/2. All right. Okay. Now, 1 is equal to n sub n. And that is this, z sub n, n. And so that tells us that nn is 1 over Z sub n. And what is this n sub n? Well, it's going to be something like this. It's going to be n0 plus lambda n1 plus dot 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 on n0 plus lambda n1 plus dot dot dot. And so its lowest order then, this nn, which is 1 over Zn, is equal to 1 plus lambda squared n1 n1. N0, of course, is perpendicular to n1, as you can see from these various expressions we've derived here. Do you want me to show you why n0 is perpendicular to n1? All right. So that's our expression. And well, what is n1? This is then 1 plus lambda squared. We have expressions over there for n1, and that is n0 v pn over en0 minus h0 squared times v times n0. And let me just erase this and get some more space here. And so that tells us that Z sub n is equal to, and of course this is approximately equal to, let me do Zn inverse, because that's what we're dealing with now, is 1 plus lambda squared, sum over k not equal to n, Vnk epsilon squared over En0 minus k0 squared. Well, at least we know what the sign of that is. It's positive. And moreover, the whole thing of perturbation theory, by the way, is that we're thinking of lambda being so small that it dominates everything. And so despite the fact this is an infinite series, we're going to say this is small, because it's multiplied by lambda squared. So that tells us that Zn is approximately 1 minus lambda squared times the same thing, k not equal to n, v kn and k squared over En0 minus k0 squared. So that's our expression for Zn. As lambda goes to 0, it just goes to 1. And it's also clearly less than 1. And so remember that Zn itself is equal to n sub n, n0, absolute value squared. That's here. N0, n sub n is Zn to the 1/2. So this thing is the probability that the overlap between the nth eigenstate of H0 and the exact normalized nth eigenstate of N0. That is, of course, less than 1 as we expect, and it's this particular expression. And so the stronger the coupling is, then the more N0 leaks out into, or the more the other levels have to come to play a role in the exact eigenstate. So the stronger the coupling, the more other states, and the less the contribution of N0. All right, and then finally, one other thing that we can do is we can look at our formula for En. And It's equation 34 in my notes here. Where is that? Yeah, this expression right here. And we can see that this expression here is a derivative of En0 with respect to En with respect to En0. In other words, this Zn, in fact, is partial of En with respect to En0. But we only computed this to second order here. In other words, all this computation was from just taking the lowest order terms in this huge inner product. But this is in fact 1 minus lambda squared sum dkn algebraic squared over En0 minus k0 squared. All right, so that's the end of the story for the non-degenerate case. We have time, I think, for an example and for a few more remarks here. How would we do this if we weren't doing perturbation theory? What's another way of going about finding the eigenstates and eigenvalues of a Hamiltonian? And one way is to say, well, you just take, you would do the following. You'd make a projection operator again. And I've used up P as a certain projection operator. I want to use something else. Let's use pi. So we have pi sub n is going to be the sum k equals 0 capital N k0 k0. So we're just going from the ground state up. This is a projection operator on part of the Hilbert space. And we can then say, we can call h hat, is h hat sub n, say, is pi hat h, pi sub n h pi sub n. So this is, what we've done is we've effectively taken this mysterious full Hamiltonian and we've turned it into an n by n matrix, effectively. And now we can talk about solving the character, I forget what the name of this is, but you know, h sub n minus e times the identity. This will give us all of the eigenvalues of the Hamiltonian. And this is not crazy, especially with modern computers, as long as you can find, and these states don't have to be the eigenstates of the bare Hamiltonian. They can be just any convenient set of states that are, say, orthonormal to make things simple. And then you just take, you truncate, so you make this a finite dimensional problem. Once you have a finite dimensional problem, these computers can whack that away as long as you can compute what the hell this is. You then, in other words, as long as you can compute h hat kl, which is this k0 h l0, as long as you can compute these for the first 10 or 100 or 1,000 or 10,000 values. And this, anyway, let's just imagine this is a Gedanken experiment. I actually used an early version of MATLAB to carry this out for an anharmonic oscillator. And what happened was the results were that for the low eigenstates, the answers were superb. But as I got up to, suppose it was 100 by 100 matrix, as I got up to maybe 75 or so, there were spurious states that started to come in. And It's kind of interesting. Anyway, as you let the size of this thing go to get larger and larger, though, typically the values you get for the low states are extremely good, and the eigenvalues are extremely good. Yeah, all right. Another way of writing this, let me just do this quickly then. You saw we have this plus Pn over En0 minus H0 lambda b minus delta n. And that's our basic equation. We can rewrite this pulling the n over to one side as 1 minus Pn over En0 minus H0 lambda b minus delta n. We use light brackets like that. N equals N0, and that tells us that n is 1 minus Pn over En0 minus H0 lambda b minus delta n inverse N0. So that's sort of a closed form solution. And you can, the inverse of something like this, well, that is just a sum k equals 0 to infinity p sub n over En0 minus H0 lambda b minus delta n to the nth n0. So this gives you a formal expression for the unnormalized exact eigenstate of the Hamiltonian. Okay, that's that. Any questions? We've got a few minutes. I don't know if we can squeeze in this example. So if somebody would like something explained more clearly, we've got 4 or 5 minutes to do an explanation, or I can try to do the example. All right, the example is the quadratic Stark effect in the ground state of hydrogen. So as usual, we have our p squared over 2 mu, the reduced mass, minus e squared over r. And the potential term times the dimensionless parameter is going to be E z. So I guess the lambda, well, I don't know. I mean, it's, you have to sort of restructure that to get E, but anyway. So E is an external electric field. And why is this, what's the first order effect? Well, the first order effect, 1, 0, 0 on the ground state, 1, 0, 0 is just 0 as we saw last time. And so delta 1, 1 is 0. I guess we're using 1 for the ground state here, and then over here I used 0 for the ground state. Maybe it'd be better to go 1 to use 1 for the ground state. Anyway, I don't know. It's not important. What's the second order correction? Well, from the formulas that we derived, the second order correction to the ground state, 1, 0, 0, is going to be e squared, a sum n not equal to 1, all L and M, NLM, Z, 1, 0, 0, absolute value squared over E1, 0 minus En, 0. So that's our expression. And you see these guys are all greater than that, so this is of course negative. All right. I don't know how far we're going to get with this today. Well, let me just define the dipole moment. The dipole moment is going to be the mean value of, in any state, it's minus ER psi, where E is taken to be positive. And we've got our formulas for, I'm trying to avoid writing them down again, but our formula here for psi will be 1, 0, 0 plus EE times the sum n not equal to 1, all LNM, NLM, NLM, Z1, 0, 0, divided by E10 minus En0. And of course, En0 is a very simple form. And so the dipole is the inner product of these, the mean value of the orbit, the position vector in this state, and the mean value in of the ground state, of this in the ground state, of course, is 0. And so what you've got is you get these various cross terms. And I think I'm going to stop there and just start again because I don't want to keep you guys over time. So I'll just do the second order spark effect on Wednesday. And so any questions?